Hey everyone, and welcome back to the Information Bottleneck podcast. And as always, we have my co-host, Ellen. Hey, Ellen.
Hi, Ravid. Hi, Philip.
Hey, Ellen. Hey, Raveen.
So today we are going to talk about a lot of different things, mainly representation and what does it mean to have a good representation. And for this, we brought the expert of representation learning, Phillip Isola, a professor at MIT. Hi again, Philip, and thanks for joining us.
Yeah, thanks for having me.
So I think we can start from representation and representation learning. So maybe tell us, what does it mean, representation learning? Why it's good? Anything that you can think about research for representation learning?
Yeah, I think representation learning is really an incredibly broad topic. Maybe the way that I like to see it is coming up with a view onto your data that is useful, that surfaces important properties, and allows you to really easily make inferences or do subsequent problem solving. So how can you take your raw data and transform it into a format that is easier to work with in some sense? And to me, deep learning, there was an era when it was kind of synonymous with representation learning, like the iClear conference was on learning representations, and it was basically deep learning. So that really is the core of so much of what we do these days, is how to come up with transformations from your data layer by layer to representations that are maybe linearly separable or surface good properties that are easy to use.
So yeah, okay. So representation is a very broad topic, but why we should care about representation?
Yeah, I think the choice of representation can make problems dramatically easier or harder. One classic case is the Fourier transform, the changing a signal from the time domain to the frequency domain. In like classic signal processing, when you're in the frequency domain, certain operations just become really easy, and if you're in the time domain, they're hard, and actually vice versa. And I think it's the same with all of representation learning. It's always about changing what is easy and hard. And with the right representation, sometimes a problem just becomes trivial. And with the wrong representation, it's really difficult. But it's always a trade-off. It's like you gain something, you lose something. So depending on what problem you want to look at, then there's oftentimes like a good representation. I guess the kind of one of the holy grails, or one of the things that we're all after in modern AI, is the generally useful representation, the representation that for all the things that humans care about doing, it's a good starting point. And maybe that's what that's the foundation of foundation models, is a good starting representation for a lot of things.
Well, related to that, I start wondering, is tokenization and the study of it a form of representation learning? And especially because models have not escaped it, despite Karpathy and others saying that it's the root of all problems, right?
Yeah. No, I think I like to think of representation learning very broadly. So I would count tokenization. That's the first stage of the representation processing, converting the raw data into some tokens. And yeah, I think that you can apply a lot of the kind of the theory and the machinery of representation learning to that part as well. But it's always like a choice. Where do you choose to like define or intervene on your representation? And maybe the tokenization layer is not the right one. Maybe you want it to be after 10 layers of processing, or a more end-to-end approach. And I think there's a lot of momentum toward that now too.
So what does it mean actually, like a good representation, right? You said it like, yeah, it's a useful representation for many tasks, but can you try to be more specific? Like what we actually care, like, I don't know. We are just like trying to taking representation and just like somehow like evaluate it on different tasks, or there is something different that we can do?
Yeah, that's a really good question. I think that you can come up with other metrics or notions of what a good representation is. I mean, I do think ultimately it's the proof is in the pudding. It's in the application. So ultimately, a good representation is one that allows you to solve real problems. But then that doesn't really tell us much. I think half the battle is coming up like, what is the right objective for representation learning? And there's a lot of ideas there. Like one starting idea is you want a representation that's predictive of the future, because all we really care about for making decisions and doing optimal control and we only care about the future because the past is the past, right? So you want a representation that contains information that is predictive of the future. So that's just one example. That's like the idea of predictive coding or predictive representation.
Do you think we can describe or qualify representation without any downstream task, right? Because, for example, like we had, I think it was ICLR last year, a paper that we looked on the matrix entropy of the layers in LLMs, right? Matrix entropy is basically you look on the distribution of the eigenvalues of the
Yeah.
covariance matrix. So in principle, we didn't look on in this case, we didn't look on any downstream task, and we say good representation is something that you can that basically transfer a lot of information of the input, right? The eigenvalues are quite spread. Do you think it's also, what do you think about it? Do you think this is true? There is some kind of representation that is good for any downstream task that we really care about without actually measure it?
Yeah, I tend to think so. I mean, I think there are certain kind of notions of no free lunch that you can come into in theory, but I don't think they actually matter that much in practice because the set of things humans care about is not all possible mathematical problems. It's, a subset. Yeah, I mean, I guess you know this better than I do, Ravid, but the title of this podcast, the information bottleneck, that was a whole theory about what makes a good representation. Capture information about the input that it tells you something about the output. This matrix eigenvalue thing, I don't know, I'm not familiar with that specific work, but that sounds similar. You want to maximize the information going through your bottleneck, going through your kind of finite capacity channel. Just to kind of maybe give some of the high level terms that I like to think about. I think one is you want a representation that has a lot of information about the relevant variables. So maybe it is explanatory or predictive of the future. But two, I think you also want it to be concise. So one of the ideas, and again, it's information bottleneck is one angle on this, but kind of you want a minimal and sufficient representation. That's one of the frameworks that people have thought about. I don't want too much redundancy because this will just cost me memory and time. I want to have a nice parsimonious representation, but I also want it to be not throwing away the actually useful information that I need to solve my task. So those are two of the key ideas in my head: is minimality and sufficiency.
And related to that, I know there's this notion, of linear separability, and also of the XOR, right, operation, and certain types of very simple models like the base perceptron, I think, where being able to solve it, but other kinds of very simplified estimators not being able to. And so I guess I'm just curious as to how this interacts with representation learning, and similarly, I guess the concept of just featurization in general, especially for the good old tabular machine learning, where you start looking back at old school stuff like one-hot encoding, for categorical values. And so what are your thoughts on these things?
Yeah. Let's see. So I do think that a lot of the kind of older ideas in what makes a good representation were a little bit too abstract. They were you want to maximize entropy, and that's not quite enough. You can have the raw data itself is a maximum entropy representation of the data. And so if your idea of representation learning is somehow capture all bits, then just you shouldn't do anything. So I think some of the information theoretic things didn't quite go far enough. And really it's more about, with stat, that's one angle, but that's a very kind of coarse angle on it. And then it might be more about the specific geometry, like the interrelationships between the data points you're encoding. What is the similarity structure in the embedding space? How does the embedding space cluster and organize data? So these more geometric concepts, I think, are really important too. And yeah, that might connect a little bit to tabular representations, one-hot encodings. These things probably are useful more due to sparsity, geometry, disentanglement, things that are beyond just the kind of information perspective.
So try to explain us. So like what you actually like, how current methods, like let's start with vision. I think maybe it will be the easier ones, right? At least in my head, vision is like the most closest one to representation, and it's easy to explain. Like, okay, so how actually now I'm training a model, yeah, probably like maybe a classifier or like say a supervised or like something like that. So what do you think, like what, like how the I don't know, cross entropy laws bring us to a good representation? What in this like mechanism, what are the important components and how they actually bring us to a good representation?
Yeah. Okay, so vision is great. That's like where I've done most of my work, and I kind of see like what is perception? Perception is, to me, basically mapping from the world to a good representation of it. Perception is just the representation learning problem. So I like to think about that a lot, um, and I would actually say that I don't think the image classifier is necessarily going to get you the best representation. So an image classifier will try to get you a representation that right before the last layer of the network is linearly separable. So the last layer can be like a linear classifier. And it is pretty remarkable that can go really far. But if I only have a few classes, then I might get this sort of collapsed representation where it's not capturing information about all the other classes that I might care about or other tasks. So it's a little bit too narrow, too specific to classifying cat versus dog, if that's what you train. I think the kind of remarkable thing is that if you train a classifier on enough classes, this started happening with the image around ImageNet when people would train on 1,000 classes for ImageNet. Then the representation starts to, like, the 1,000 classes is enough to get you kind of a good, a good basis for a lot of tasks in vision. But I still think that was just like, you want to go to infinite classes, really. And that was where maybe the field shifted more to the unsupervised or self-supervised recipe, where you don't have a discrete set of classes, but you want to predict something that is a lot more nuanced, high-dimensional, continuous. Maybe you're going to predict the next frame in a video, and it's kind of like an infinite number of classes. And that, those methods are the more the modern way to do that leads to better representations.
Like, what are the components that actually
Yeah.
like bring you there? Let's assume now you're training your favorite SSL with your favorite SSL method. Like, how we get like good representations?
Yeah. Okay. So one lens on it could be from contrastive learning. It's one of the popular SSL methods. And in that one, you're trying to align two views of the same thing and push apart two views of two different things. And so you can see a cross entropy classifier is kind of a special case of that, where it's trying to, if it's a cat versus dog classifier, it's trying to align all the cat images should map to the same point in embedding space and representation space, and all the dog images should map to the same point, but these points should be maximally far apart. Like we had some work years ago on this where we tried to kind of model contrastive learning as two terms, alignment and uniformity on the hypersphere. So these methods would be normalized so that they're mapping the input data to vectors on the hypersphere. And then you can understand the loss as having those two terms. One is align two things that are the same and otherwise push everything apart. So it connects to all the things we're talking about. So it's information maximizing in a sense, because the max entropy distribution on the sphere is uniform. So it's spreading everything apart on the sphere like maximizes the information that you're encoding. But it's also in a way tuned to the downstream task in the sense that two things that are considered the same, and that's kind of a modeling decision. You have to decide what counts as the same. But if it's two things with the same class, then that's your notion of sameness. Those get mapped to the same point, and so you're getting a representation that's invariant to things that are within class variation.
What's your opinion on dimensionality reduction techniques and also clustering and the general notion of unsupervised learning? I always thought that was especially elegant and something that I think would be totally up your wheelhouse.
Yeah. No, I think that I like that stuff too. So that's kind of like the dimensionality reduction is about some minimality or compression. I think these days I feel like dimension is not the best lever we have for controlling complexity. So you can have a high dimensional representation, a high dimensional embedding space where the data gets mapped to a low dimensional subspace or a low intrinsic dimension manifold. The dimensionality doesn't tell you. It's a constraint on the complexity. Maybe it's like a bound on the complexity. So you could have something that is in high dimensional space, but is actually simpler than that would suggest. Or you could have something that is in low dimensional space, but the numerical precision is so high that if I have like an infinite dimension, infinite numerical precision, then I can have one dimension that just loses no information. It could be a very, very complex mapping, like I think some cryptographic mapping from like the data to just a number, a floating point number with infinite digits. So I think dimensionality is not quite the right notion. There should be some other measure of complexity and some other controlling complexity. I don't think we actually have it yet. I don't think it's entropy or sparsity or the L1 norm or the L2 norm. I don't think we actually have it. I think it's still something that we're, as a field, trying to come up with. My favorite things to think about in that direction are more like algorithmic complexity, like Kolmogorov complexity, but I don't quite know how to formulate that. I think epiplexity is one of the new ideas in this space. There's a bunch of ideas.
Yeah. Epiplexity is like from Andrew Wilson,
Yeah,
right?
from Andrew Gordon and Wilson, yeah.
But and what do you think about compression? That like at the end, I did some work on compression in the past, and like from information theory perspective, we found different things. And in information theory, there are a lot of debate about estimators of information and things like that, and clustering. But at the end, I feel, and I think this is like the mainstream point here is that like, yeah, you have kind of like geometrical clustering, right? That like during the training, like you start with like that all the points are in some very high dimensional space, and like during the training, like you have this geometrical clustering, and you can call it like in different ways. First of all, do you agree? And if so, what do you think is actually bringing to this clustering, and if it's important for representation or like for downstream tasks?
Yeah, I do agree. I think that's actually the structure that I'm particularly interested in, is the similarity structure. So what is the relative distance from every data point to every other data point, and which data points belong to the same cluster? Which things embed near each other? Do cats embed near other cats, or do they embed near dogs or elephants, right? So it's the similarity structure, and I think that's a really important way of characterizing a representation, because it tells you things about what you can do with that representation downstream. It tells you how the features will kind of generalize. Like if you train a model on top of those features, then two embeddings which were similar in that feature space will probably be somehow treated the same, because models are smooth. The downstream model is smooth, so it will somehow kind of, this is how you will generalize across different data points in that representation space. So yeah, this similarity structure, this clustering structure, and maybe this gets a little bit at this kind of line of work that we've been doing recently, that where we've been looking at how different models seem to converge on the same representations. This platonic hypothesis that we've been writing about. And one of the most kind of striking versions of that is that the ways different models cluster the world seem to often be alike. And it kind of makes sense. Like every model is going to put all the cat images into one cluster, because cat images look the same. They're found in the same places. They behave the same. And so, yeah, to me, this is a really good toolkit. This kind of looking at the clustering structure. Ultimately, it's because my belief is this is because that's how the world works. There are clusters in the physical world in terms of our experience of the world.
So I have many questions I want to ask about this now that hypothesis is coming up, and I'll point out, I believe it in the sense of that's what the data is, but I don't like it as somebody who's really into Max Stirner, as a philosopher who's really hardcore, like anti-Platoist, philosophically. I guess my question is, I've been telling investors that the Platonic representation hypothesis among, there's this meaning around, representations are easily alignable, similar to each other, right? Which I think is the meat of that paper. But what I remember was a lead buried in there that I hope I'm not hallucinating, basically showing that if you train models on hate speech, they generate bad code and vice versa. And I've seen that reproduced in a lot of AI safety literature. And so I've been telling investors, and I'm hoping that that's why they're declaring Anthropic the winner, right? But I've been telling them that Anthropic cares more about AI safety and alignment, and therefore their models are better for code generation in enterprises and reducing the risk of prompt injection because they absolutely refuse to engage with like risque content or taboo content. Is this correct? Like, is my way of kind of explaining this like correct, or would you disagree with this in any way?
Yeah, interesting. So I think that we didn't actually have that result that training on hate speech leads to worse coding models, but yeah, I've seen. So is that the result that you're referring to?
I maybe I saw it connected in a
No
paper
worries.
that
Yeah.
was citing this, to be fair, right? But I've kind of connected these two ideas for people.
Yeah, no, I think people have, for me, we put out this paper, it was a position paper, and it's quite broad, and then people have taken it in a lot of different directions. And the basic question we were trying to ask is, when and why do different models converge on similar representations? But I definitely wouldn't say they always do or that they always don't. It's somewhere in between. Um, and I think that the evidence is stronger for convergence more in terms of like convergence on physical attributes of the world, like different models will represent the physical world in the same way, geometry in the same way, because that's a very strong that physics is we assume true that there is a way the world works, and all these models are seeing that it's a very strong signal. In the space of more social convergence and alignment between different types of speech and toxic behavior versus coding versus math, I, I haven't seen evidence myself that that I want to say like these are all converging to exactly the same representation. I think that feels more. I know there's a lot of papers on this, but it feels more. It's still kind of in this kind of vibe space of it feels like all the different language models we interact with have kind of the same personality, but I'm not quite sure if that's been carefully measured or if this is, because of the arguments we were making about representational convergence or more about post-training and all the companies have the same, safety teams and policy teams.
Our anti-slop work definitely looked at how model outputs are very similar based on their slop profiles. I have just one quick follow-up question, which is that there's this follow-up paper that I'm sure you're very familiar with titled Revisiting the Platonic Representation Hypothesis and Aristotelian View. What's your opinion on it and their results? My understanding is they conclude that models exhibit local neighborhood structure, right? Which is like a weaker claim than that they're getting similar representations. It's like partially similar, I guess.
Yeah. I think it's a great paper. So it kind of goes back to saying that the strongest evidence might be about the clustering structure, which is more about the local neighborhoods. Like different models agree on their nearest neighbors, but maybe not about their global distance structure. And yeah, I think that paper added a lot of nice nuance and some new clarifications to the Platonic hypothesis. I'll also say that it's very much in line with what we kind of had in mind. We chose in our paper from 2024 used this metric based on are my nearest neighbors in my model the same as your nearest neighbors in your model, and it was We chose that because we saw that the global distance structures were not aligning that well using the previous measure called CKA, which is a very popular measure. And so we were like, no, we think it's more about these local nearest neighbor relationships. We didn't fully articulate that argument. And so this new paper kind of went in depth onto that and really clarified things. I think it was really nice.
But so what do you think are the factors, like are the main factors that actually affect it, right? Do you think now we will, I don't know, if we're in LLMs world, or like if we are training on different environments, or like post-training it will affect the representation, or like maybe like the pre-training has better like or like stronger effect? Or this something like that related more to vision, right? To this physical world?
Yeah. So, right, like what, and that's basically the research program that I'm trying to work on now is, so not to say everything is converging. That's like a strong version of the hypothesis. It's fun to state a strong version, but it's not what I truly believe. It's to identify what are the commonalities, what are the convergent forces, what are the kind of universals between these different models? Because I think just those are the interesting things to me. If we can identify those, they have a lot of explanatory power. It's like in physics, you want to find the universal, the unified framework. So wait, sorry, yeah, review. Can you say the question
So
one more
what are
time?
the factors? What are the factors that actually affect it, and how they affect this representation? And if you think that these are like related to the type of
Right.
of the data, for example, physical world signals versus language.
Yeah. So I think there's a few cases where you get stronger convergence and some that you get weaker. And I think one of the cases where it's stronger would be when it's convergence on truth, convergence on the true state of the world, whatever that means. Okay, I'm going to set aside the philosophy of like, is there a physical state of the world or not? Are there facts or not? Let's assume that there are. Then I think it makes sense that all these models, they might, maybe you can ask them to lie, you could post train them to lie, but it's hard to prevent them from discovering from an intelligent system from discovering truth, because truth is the consistent variable that minimizes loss or perplexity, whatever you want. Like it is the latent variable that allows you to predict the next token accurately. So yeah, I think all these models, it's not surprising, or we should expect that they will become more and more factual in their representations and in their latent knowledge, maybe not in their behavior, because somebody could always post-train them or prompt them to lie. But I think there's a reason to expect that they'll know how the world works, and then it's our job to surface that. But I don't think we'll have convergence necessarily on the space of possibility, on the space of creative writing, on the space of designing a new building, on the space of art, on the space of synthesis, of engineering. If I want to get a model that will design a new space station or a new protein, this is the space of possibility. There's no example of that in the world. It's not like it's a physics law that everybody kind of has to agree, because there's only one law that is consistent with the world. And so I think that's often more the regime of post-training, where you are adding a personality to your system, you're asking it to do some new creative task. And I think you could have some convergence there or not, but it's much more debatable. And so I think for the pre-training on understanding the state of the world and how the world works, that's where I'm expecting the most convergence.
You don't feel that, like, I don't know, even for vision, right? That it's kind of like physical signal, right? Like if you see two cats, basically my brain is filtered out that like classified as like two cats, right? There are no real, like, I don't know, similarity or something like that, like physical similarity. It all the things that we are actually seeing, like actually classify as close to each other, goes through our brain, our perception of what is similar and what is not. Do you think there is something like true similarity in the world?
Yeah, I think there's something maybe close to true similarity. I like this idea that the cat is not an arbitrary word. We have that word because maybe it's a so-called natural kind, or it is a thing that any intelligent organism, the Martians, if they had cats, they would have a name for cats. If they come to Earth, they'll come up with a name for cats. Because there is this thing, this space-time event, the cat, that where all the features of the cat co-occur in space and time that is temporally smooth. Like the cat at one instance is, adjacent to the cat at the next instance. It doesn't teleport around. There is this underlying smoothness. And I think from fairly simple assumptions of trying to do unsupervised learning to try to make sense of the world with a finite machine, you kind of get these natural groupings that are they're the first principal components. They're the k-means clusters. They come out of statistics. Cats, the word cat is not something that humans just arbitrarily made up. It's something that really is a mathematical entity in the world.
Well, I'm curious too. Have you heard of the Bouba-Kiki effect?
Yeah.
Yeah.
I love
What do you think about that in relation to all of what we've been talking about?
Oh, that's a great question. I think that it could be for similar reasons. So I think the effect, if I remember correctly, is most humans will look at a spiky object and think it's more associated with Kika than Boba, and a
Yes.
blobby object will be Boba. And that could be because there's cross-modal convergence, like the sound Kiki to Boba is the same geometric relationship as blobby to spiky. It feels to me like it might be a little bit of too much anecdotal. Like maybe there's some other cultural reason for this, but I think it's at least consistent with the idea that there is convergence onto these kind of natural kinds.
So I assume that I know the answer, but what do you think about world models, or like world models versus autoregressive LLMs or VLMs?
Yeah, so I really like world models, but again, maybe it's similar to representation learning. I kind of think everything is a world model, so I don't I don't make super hard distinctions between these things. So so I think that this is a place where maybe my opinion is a little bit less common. Is that I think LLMs are pretty close to what we mean when we say world model. And behave in ways that are not so different than world models that are trained to be world models. Like there's some people that train models that have a transition function and predict the next state of the world and apply it to reinforcement learning. And I think that what an LLM is doing when you auto-regressively roll it out is different in some ways, but maybe of the same kind.
Yeah,
Do you have
actually,
Oh, sorry.
no, actually, like this is Stefano Soato was in the podcast I thought 2 months ago, and he claimed basically the same thing, that we don't need explicit world model, and actually LLMs are good enough world models.
What do you think of like diffusion LLMs and I guess similar the reverse like autoregressive image generation?
Yeah, that's a good question. I haven't thought too much about that distinction for language modeling. My so again, I'm always kind of trying to look at the commonality. It's just my bias, and there's for sure it's equally valid to look at the differences between the models. But I think there's so much commonality that I'll take that perspective. That I think that the autoregressive LLMs are can be considered a special case of a discrete diffusion model where the masking sequence happens to be in raster order. This is a perspective that a lot of people have pointed out. I think Deepak Pathak has some nice recent work understanding a diffusion model as a data augmentation on the masking order of an autoregressive model. So I guess I think there's a lot of commonalities. And I think that both of them share this property of take a hard generative modeling problem and decompose it into a lot of really simple steps that maybe are like Gaussian steps, like just predict the next token. So yeah, I like to look at the commonality.
And what do you think we'll see like converge to, or like as we saw till now, it's like converge to, I know from 5 years from now, what will be the models that we actually will dominate, right? We'll see more autoregressive models, or do you think that we'll see, I don't know, can be diffusion, can be JEPA style models, like whatever? And how the future will look like, and also like what are the important components do you think that like these models should have?
Yeah. So I think that I don't have a strong bet on diffusion versus autoregressive, JEPA versus, masked pixel modeling. I think that it's good that people are pursuing each of these. Maybe one that I feel like I'm placing my current bet on is RNNs making a comeback. I think we're already seeing a lot of forms of that. But I still feel like the model, that the new architecture that is this RNN like that really nails it and is clean and simple and everybody agrees is the new thing, the thing that replaces transformers. I think we haven't quite seen that yet. I feel like this is going to be critical because RNNs have this property of unbounded memory, and it just seems hard for me to imagine that all of intelligence, human level intelligence, superhuman intelligence can be done by just like increasing the context window. Now, it might be the case that the RNN is of the form where it is a memory.md file that a language model is writing to and reading from. That's fine. I just think it's going to be something that we'll understand as like an RNN.
What do you think about the need for continual learning?
Exactly. Yeah, that's very much like why I believe in RNNs. I think continual learning is a big thing. It's important. Doing it all in context feels limiting. The context. Can I really do continual learning for an entire human lifetime? Or maybe we're having super intelligences that live for trillions of human lifetimes. Can I do that all in just a big context window? Seems unlikely. So I think that having persistent memory that can be read from and written to is like my guess is that's the thing that's going to unlock continual learning, or that will be one key component of it.
But do you think that, so I don't know, a few weeks ago, there was Yaroslav Paluto in the podcast, and he claimed that at the end, it doesn't really matter. Like, we are just trying, like he called it that we did in the past, gradient student descent, right? That,
Yeah.
like a lot of different ideas and without very principled directions. We just tried a lot of things. Some of them work, some of them didn't work, and then we converge to something and we can do it again, but there are no like principles that we actually can rely on them. Do you think it's true?
I think there's some truth to that historically, but I'm more optimistic. I actually think that there are principles. In fact, I would say that I think there's kind of a narrative out there, or a feeling that we don't understand intelligence, that everything is a big hack, that we don't understand the human brain, that we're pre-Newtonian, that the frontier labs are just building a big kludge on top of. I actually I kind of see it as, no, we're making a lot of progress. Like, we have these principles and they're working, and the scaling laws are somewhat holding up, and there's still mystery, but I feel like we're actually kind of in this golden era of the science of intelligence, where we just understand so much more than we used to, and we're understanding so much more each year. And very often I actually find that, with my students working, like, we have some idea just from these kind of principles that people have come up with, and we formulate it on a Gaussian mixture, just a toy thing, on some MNIST data, and we can kind of work it out, and it actually does generalize. It actually does, it does scale. It does hold up. So I actually think that we're not just in this hacky regime that sometimes it feels as caricaturized as. And I have hope that we're coming to more the science era.
But is it not frustrating because, like, at the end, like, there are these like frontier models that, again, people are trying try and errors at the end till they converge to something, and the best thing that we can do is to explain these things, right? And like not to offer now new methods that will push the SOTA results at scale. So do you think, is it not frustrating for you? It's for me, by the way.
Yeah. No, it's frustrating. Maybe, yeah, two thoughts. One is that I actually think that if you just go back to small scale, that you can run comprehensive experiments and really understand the system. you can make a lot of progress. I don't think that we're in an era where the only evidence that you can operate on is what your rank is on like LM Arena. So I do think like the machine learning theory and classical like methods in science at the scale of one, maybe eight to 100s. Okay, we have to have a little scale. I think you can do stuff. And then the other thought is that I think sometimes these frontier models, they come to be somehow, and maybe they came to be in a way that was grad student dissent or a lot of hacks or market pressures. They're like organisms that evolved, and we didn't have full control over how they evolved. Humans did some of the software engineering, AI wrote its own code. We got something, we got to an artifact, and now that artifact is of the level of complexity that, to me, it looks like the organisms that I was interested in studying in grad school, which were human brains and animal brains. It looks like an organism of a similar level of complexity. And now we can apply the natural scientific method to it. We can be neuroscientists. We can go back to studying it as a new, a new creature that we can probe and we can test. Now we can actually probe in ways that you can't with biology. You can do it all in the space of digital code. And we can make a lot of progress on understanding these things. So it's kind of like, yeah, maybe these things did come to be in some somewhat hacky or poorly understood way. But now that they came to be, we can do science on them. And that science can be so much faster than on neural nets that are actually biological.
And what is...
I was just going to probably ask about the same thing about like the biological neural nets. Like, do you like spiking neural nets? Why is it that techniques that have tried to add biological plausibility have henceforth led to worse models?
Yeah, that's a good question. And maybe it's a little bit anti-Platonic. Like, okay, wait a second. Didn't biology converge to the same thing? Why can't we use those lessons? I think, okay, I really like this talk that Bill Freeman gave once. He's a professor at MIT that I've worked with. And he said it was called Feathers and Wings, and that some things from biology are more like feathers and some are like wings. So wings are a structure that we have used for airplanes, and feathers are a structure that we haven't used. And so you have to be able to pick the part of biology that actually is useful and generalizes to useful engineering applications. Some parts of biology are either like vestigial or they're operating under such different constraints compared to an engineered thing that it just doesn't make sense to take that lesson. And I think a lot, I don't know the area of like neuromorphic circuits and like neurons that are more complex than a ReLU. I don't know that literature, that area very well. But I think I'm satisfied with taking a neuron as a ReLU or a linear, a perceptron neuron. I think that might be the wing of biological neurons, and the feathers of biological neurons are the exact spiking dynamics.
But then, like, it's not clear to me how you can actually like distinguish between the two. Like, then you say, okay, so like it works, so like these are the important parts, right? But
Yeah.
it's not kind of like cheating, right? Because like you say, like, okay, what works, that's fine, and then I will try to explain it in retrospective.
Yeah. Oh, absolutely. I wouldn't say people should not work on that, because you have to take the bet and see. And yeah, maybe we only know in retrospect what was the feather and what was the wing, and we still don't know. Maybe like the spiking dynamics, the spiking neural nets, it turns out it is one of the wings. And so I totally hope people do look at that too.
Do you think we can create artificial models that work similar to the brain in the near future? Or like at the same level, at least, as the...
Do you mean in terms of the functionality or in terms of like the neuromorphic architecture?
So both, actually.
Yeah, I think I'm somebody that kind of believes or feels that we're in many respects close to human level intelligence. Not on it's jagged, not in all respects by any means, but okay, I'll just say I really like this Marr hierarchy. This is another one of these neuroscience notions. David Marr was a neuroscientist who came up with these three levels of analysis: the computational level, the algorithmic level and the implementation level. And the implementation was like the hardware, the wetware. And I don't think we're close to making artificial nets that are anything like the implementation layer of the brain. And I don't know if that's important or not. My guess is it turns out to be more like feathers, but maybe not. I hope some people try. But then the algorithmic level is like the circuits and the like this mechanistic interpretability field really loves to get into this layer. Maybe it's also something about some of the representational geometry properties I've talked about. And then the computation layer is like the input-output behavior. What is the mapping that the intelligent organism is doing? And I feel like the computation layer, you can make the best argument that like human-like abilities, we're really getting close to matching the human mind, but it's only on one layer of abstraction. Now that is the layer that matters for like utility, I suppose. Like that's when you can actually automate a human ability for better or worse.
But do you think we can take ideas from how the brain actually like behaves or like design or like even how human things about I don't know the structure about like the world and to implement it in order to get better models?
Maybe. I think that we can. So yeah, I think people should try on all levels. My guess is that the implementation level is not going to lead to major breakthroughs in AI. I think the level 2, the algorithmic level, there's going to be some insight that comes from that level. I think famously the idea of convolution partially came from Fukushima and Jan LeCun and others, like borrowing this idea of receptive fields, algorithmic structures within the human brain. And I think the computation level for sure, like that's what all of our benchmarks are designed around. It's like, here are some human abilities. Let's see if the machine can do these things too. We don't just give them some random arbitrary string math problem and say, can they like match this string, right? Or actually we do sometimes, but not very often. But maybe I would say that, yeah, like I did my PhD in Cog Sci, and for a long time I did think that I wanted to study the human brain so that we could come up with principles of intelligence that would be useful for AI. And these days, I'm less optimistic about that approach, but I think there's something beautiful that happened instead, which is that just designing AI systems to do the job of AI, like next token prediction or image classification, you end up learning similar structures at layers at Marr level 1 and 2 as the human brain does or as a monkey brain does. And so you have this convergence means that you kind of get it for free.
But because like we just so we talked with Tal Linsen from NYU, and he said like actually the opposite, at least in like in cognitive science and like these areas, that like yeah, that's true that like at some point like when the model become better, like they are like similar to human, but like at some point, like when they become better, they actually started to behave different than humans, and like actually they behave very different from humans when you go behind some level of performance or capabilities. Do you agree with that? Do you think like this only like in some areas and like some subdomains?
Yeah, no, I think that's there's probably some truth to that, but I think that it depends a lot on the regime you're looking at. Like what might be happening is that if you really zoom out from perceptrons to Opus 4.7, from like an amoeba to the human with the human brain, like at that scale, I think that we're going to see some kind of convergence, like similar patterns and strategies kind of they become more and more alike as you go toward that more complex system. But then maybe just in the last year or two, there is deviation from the trend. So I don't think it's like everything will have to always converge. But it's like when you really zoom out, then you see it most strongly. So I think I've seen some work that suggests that in recent years, language models are becoming less aligned with the brain. And this is also true for this kind of platonic story. We looked at cross-modal alignment between vision models and language models. And some of the recent models you see are reversing the trend where they're becoming the language models are becoming less aligned to the vision models. I think this could be temporary. This could be just, it's like Simpson's paradox. Like there can be anti-correlations within a broader, longer-term correlation. One thing that we've been looking at recently is the effect of post-training, and it seems like the post-trained models, part of the explanation of this lack of continued convergence is that post-training really changes the story. So I think the jury is out on this. I don't think. I think that we're seeing some cases where things don't align, but they're on like the year-long time scale, and we'll see what happens over the next 5 or 10 years.
So do you think everything will be pre-training at the end, or do you think we will still see post-training for a specific task? Because again, my perspective is like pre-training is, let's get good representation, and then post-training, let's try to align it for downstream tasks. But do you think if we have good enough representation, right, like at the end, we don't need post-training?
Yeah. I think I'm definitely a fan of like pre-training is all you need. Everything is about representation learning. That's just the lever that I like to pull on. But I think it's not about, you only need one or the other. I think pre-training is roughly sufficient to solve things, and post-training is sufficient to solve things. But sometimes one is more efficient than the other. And so it's like there's these two levers you have, the pre-training and the post-training. Maybe you have some other levers too. And I think there's going to be a lot of cases where you would really want to do it. The post-training is a very heavy lever. I just say that I tend to think the pre-training has always gone farther than like there was an era 10 years ago when people were really focusing on end-to-end trained systems to solve the objective function that the system is trained to solve is the same as the actual task, the thing they're going to deploy it for. And I thought that wasn't quite right. I thought, no, we really want to put most of our effort on this unsupervised learning phase before we even know what the task is. And then that went farther than a lot of people expected. And I think we're kind of coming back to maybe a similar mistake, if you would call it that people are now saying, okay, pre-training is done. We're out of tokens. We got to put all the effort onto the post-training phase. But maybe actually, we're not out of. Maybe just more and better pre-training can continue to get you farther. We have a new paper I could talk about. This neural thickets paper. We just put this one out, and in that paper, what we're arguing is that pre-training takes you to a regime of your weight space where nearby solutions to downstream tasks are quite easy to find. So the gist of the argument, or it's more of an empirical finding, is that post-training can be easier than people thought. Like this idea of you get a general purpose representation, and then you have to do a ton of like RL to adapt it to do some complex new behavior. That might have been exaggerated a little. In fact, these pre-trained representations, as you scale up the models, they become they kind of contain and they have a latent behavior that you can pick out quite easily that will do this thing that looked like we thought maybe required a ton of RL to find. So adapting pre-trained representations to new problems becomes easier as the models scale. So maybe pre-training is not over. Maybe, we just let it scale a little bit more.
But why do you think it is? Why do you think like scale actually make the representation better?
Yeah, that's a good question. This thickets paper is mostly an empirical observation that, the representation becomes better with scale. And, I think we've all heard that a million times by now. We have some ideas as to what is going on. I think one reason is that there are a lot of common structures between different problems. This is kind of that convergence idea that the problem of classifying images and the problem of understanding sentiment in text, they actually have common structures. They're all in this universe. The underlying cognitive machinery to solve both of them can share a lot of structure. And so that kind of suggests that some kind of convergence, that the weights, the model weights that can do one thing are near the model weights that can do another thing, because two different tasks share a lot of structure. There's circuitry that's in common between those. So the weights should be that what do one or the other should be near each other. So I think that's one reason why things you end up in this regime where all the different expert solutions are kind of near each other. And then there's another reason why you actually have this cluster of behaviors, and they don't just, it's not like you have one parameter vector. We could get into that too.
Speaking of the one parameter thing, there's the paper representation fine tuning and the techniques about getting ultra parameter efficient. And I think it also gets related to work in the like model uncensoring stuff where like safety is often found in only a few parameters. And neurons. So what's your thoughts on low rank fine tuning and similar techniques?
Yeah, I think this is all consistent with this story that post training is easier than we thought. And I think, yeah, I don't know. Often in work, I feel like I'm just trying to pick out the story that's already in the vibes and maybe characterize it a little bit more. So I think that there's a feeling, and there's a lot of papers that are showing different angles on this. That is, oh, actually, post-training can be low rank. Oh, actually, it's only a few dimensions. Maybe one parameter is enough. 13 parameters is enough. LoRA was, an earlier really popular example of that. It turns out that actually best of n is really effective. I can just like guess a few times and sample a few completions to my prompt, and one of them will be good. Like, I think all of these are consistent with that. After pre-training, the geometry around, like the lost landscape around the pre-trained weights is actually relatively simple. Maybe it's a flat minimum. Maybe it has linear mode connectivity. Like, there's so many different pieces of the story that we're like finding all over the place. And I don't think we have like quite the full theory yet, but I think these things are all consistent, and it just feels like we're so close. Like, we're on the cusp of like really understanding this thing.
And what do you think about, like, these days everyone are really excited about environments. These like RNN environments that you can both evaluate on them, like terminal bench, maybe it's the classical example. What do you think as part of like the shifting to post-training, that now everyone are training on these environments, they become super important? What do you think? Do you think so? If your theory is correct, we actually don't really need very complicated environments, right?
Right. Yeah, that's interesting. So I think it's hard to say. I think there's two reads on what I'm saying. One is that, okay, actually pre-training is all you need. After pre-training, all of these benchmarks are just epsilon step away, and you can get there really quickly. Another read on what I'm saying is that all our benchmarks are terrible. They're only epsilon step away from the pre-training. The answer is on the internet. The benchmark is just like testing if you've memorized some solution that's already on the internet. I think the truth is somewhere in between these two stories. I think, funnily enough, this idea that of the neural thickets partially was coming from this old paper by Schmidhuber and a few other authors. So he's always ahead of the times.
We just interviewed him last week.
Oh, good. Yeah.
For a double feature episode.
Yeah.
Nice. Okay, so maybe he can comment on this too. But he had this beautiful paper on random guessing, showing that in 1999, maybe sometime around then, if you take some simple benchmark for testing an RNN's ability to do, like, I don't know, parity check or something simple, randomly guessing the weights of the RNN n times, and then doing that until it just happens to solve the problem, worked as well as some of the algorithms of that time. And we're basically finding the same thing for modern LLMs, that randomly perturbing the pre-trained weights can have a high chance of landing on something that acts like a good reasoning model that solves some post-training math problem. And Schmidhuber and his co-authors said, this means that our benchmarks are just trivial. They're not interesting. They're not testing real intelligence. Okay, now we're seeing the same behavior for LLMs doing math and reasoning and coding. It's hard for me to say that's not real intelligence, but it might not be testing complex like learning or adaptation. It might be true to say that's intelligent behavior that's been kind of memorized, and it's not really, there's another part of intelligence which is adaptation to dramatically new things, and maybe our benchmarks just don't test that right now.
And do you have specific like ideas how to actually test it?
Yeah, I mean, one part of me has this slightly I don't know. Has the feeling that maybe it will turn out it doesn't matter. Maybe like once you've memorized the universe, like it's good enough. Adaptation, like I think you can always make the point that there's an infinite number of problems or like an unbounded number of problems that a human might care to solve. But I mean, maybe for some superintelligence that cares about proving all the theorems in the universe, but in my life, I don't know. Maybe there's a finite number of problems. So I think I go back and forth on this. There's a lot of people in this area called open-endedness that really feel like, yeah, there's like this open-ended, set of things that we would like intelligence to do. There's creativity, there's discovery of, and it'll never end. And I think that's beautiful. And I also kind of have done some work in that space, but a part of me is like keeping in mind, maybe not. Maybe once you have 100 trillion parameter transformer with a context length of 1 trillion, it's like it will do what makes humans happy. So I think it's unlikely, but I just want to say that like we shouldn't assume that human utility is unbounded in this way. Open-endedness is meaningful. Like adaptation is important. Creativity is important. We want to understand that part of intelligence too. And for that, I'm excited about these things that start to look more like artificial life, where you have agents in some environment, and maybe they don't have any explicit task or a single task, but they can just build towers and they can play and they can do things. And I think that so there's one approach that people have been pursuing, which is maybe like ArcAGI and other benchmarks that really try to test adaptation and generalization to entirely like novel problems. And I think that still might only be like a half step. There still is the idea that there's a correct answer, that there is a problem to solve. And I think you could be even more dramatic and say, no, you really need to get away from this idea of having a benchmark with a set of held out tasks. It should just be like, put the agents in a complex, rich ecosystem and see what happens. And so that's closer to this field of artificial life that I find really interesting.
So maybe like you start to say about artificial life. So like maybe you can describe, like, let's start to go more deeply on it. Like what is actually the setting? Like we have a trained model and we put it like and just in some like environment, and let's, without any given specific goal, and we say to it, yeah, just enjoy, walk
Right.
around,
Yeah.
kind of like Sim City.
Exactly. Yeah. It's that kind of thing. There's an old field around this, and I think one of the phrasings of the goal is to understand life not as we know it, but as it could be. And I can't remember who said that at the moment, but this is a wonderful description. Like we humans and the planet Earth are just one sample or one instance of what life forms could look like. We might have billions of creatures, but there's trillions or quadrillions or infinitely many possible creatures that sci-fi could imagine that could exist in the future. And so artificial life is kind of the study of all of those creatures. And the most famous kind of life-like form from this field, I think, is probably Game of Life, John Conway's Game of Life, cellular automata. But the field has explored so many other types of life-like creatures. So they're definitely far from the level of complexity of any kind of animal. But there's the precursors. And then I think the thing that's happening this year, which is really interesting to me, is that actually the latest LLMs, the agentic systems, are of the level of complexity that it actually feels to me like we should treat them with the same tools as we use to study biological life. And that now when they're given more agentic capabilities, when they have a persistent memory file, when they have a soul.md and they have intrinsic motivations and maybe a value system, like we're scaffolding on these things that are the other components of the brain, not just the cortex, but the limbic system and the other drives in the brain. And once you do that, then this field of artificial life suddenly is populated not by just cellular automata, but by Claude agents and other LLMs, and their behavior is really interesting. And yeah, we just started looking at that recently.
And what is the goal? The goal is like to try to imagine different paths of life. The goal is to try to see how the interactions work between different agents and like why we're actually doing it.
Yeah, for me, the goal is really basic science, or that's my motivation. Is I just would like to understand this space. What does it mean to be alive? What are the possibilities? What are but I think that there's so many scientific questions that you can study in this space. There was a nice work from a few years ago from I think Michael Bernstein, sorry, and others, looking at these simulated people in a town and kind of proposing it as a way of understanding social interactions and behaviors. Maybe we can understand how humans can solve problems or avoid conflicts by studying these microcosms, these simulations. So there are these kind of applications, but honestly, for me, the motivation is more just like pure curiosity. I want to see, yeah, before I think the recording, we were talking about this idea of abiogenesis, like how does life get started in the first place before, if you're not, most of modern AI is just distilling the internet, just imitating humans. We have this amazing repository of human behavior. We can make creatures that imitate it. But what would it look like if we don't do that? Now, it's a little circular because I'm saying that one of the exciting avenues in artificial life is to start with a distilled internet model and then see what it can do beyond that, and then put it in an ecosystem and see what cultures it creates and how it interacts with other models. And maybe we'll learn something about social science, about game theory, about economics, about anything that is more than just a single brain.
Very, very interesting. I've always imagined, AI training as trying to be almost looking at a mirror on, how humans act, and maybe it's kind of a blurry sort of mirror. Um, do you think that techniques that try to make models or AI systems that are explicitly non-human but still understandable in some way? So I guess techniques, diversity promoting sampling would be an example. Do you think that that's an important aspect of like super intelligence?
Yeah, I think that's potentially really important. Like, I would actually say that for my own career, for a long time, I thought maybe my whole career could just be about understanding human-like intelligence, and humans would always be something beyond. But now we have things that rival us in various ways and are interesting of their own accord and might start to diverge from us. Um, and that becomes a new thing that's interesting to look at. And I do think that again, like this going back to this idea of the platonic convergence, I think convergence on truth, everybody agreeing on the facts, makes a lot of sense, but converging on possibility doesn't seem like a great thing. You don't want this monoculture where we all have the same architectural designs and value systems. We want diversity. So there's these really interesting algorithms called quality diversity, which are in this space where you try to have a population of different agents that all are doing good things, but differently good things. And I think that was less on my radar a few years ago because the models were just so poor, so far from humans. But now that, like, in some domains they're rivaling humans, I think this becomes newly important.
Okay, we almost out of time. One more question, like, what do you think everyone are working on it right now, and it's actually like a wrong direction?
Oh, interesting. Yeah, that's a hard question. I think the easy answer is something like everyone's working on LLMs, or but I actually think that's the right direction. Or it's not the only direction, but I don't think there's anything wrong with that, and I think it will still go really far. Everyone's working on scaling. Like, yeah, that's great too. They should be working on that. So maybe it's not so much that I think any of these directions, any of the mainstream directions are wrong. It's more, I do wish, or I do enjoy working on the things where I feel like they're overlooked. So I think I'm really excited about this artificial life work. We have a few papers in that area, and they're not my most well known papers because they don't work. Like, it's just a crazy direction, and they don't do anything that useful yet. But that's actually often the more fun project, is the stuff that is not yet, doesn't really work, isn't popular, isn't mainstream. But I do believe that the mainstream approach is effective. It's just maybe it's less interesting, or maybe there's there's enough people doing that.
Like, I must admit, like, it really is like you really enjoy the thing that you are doing, like the research that you are doing, and it's really nice to see. Um, but like, do you think you have a lot of colleagues and friends in industry labs, probably in like all the different big labs. This is something like that you want to do, or like this is something that like you want to stay in the academia and to keep things without
Yeah. I
constraints.
think about it a lot. I have a lot of FOMO. I think academia is the right place for me. Yeah, I do love it. I think there's also really exciting things to do. I think if there's a product that I feel like can be done and is really meaningful and I believe in, then I would be happy to work on that in industry. But I think I would say that a lot of students, a lot of folks are really concerned right now about how do we compete with the industrial labs, and I think a lot of this is coming from the perspective of I'm an engineer and I want to build a state of the art system. And I enjoy doing that as well, but it's not my main motivation. Is I am a scientist and I want to understand new life forms. And that's kind of been my response to the crisis of what's the value of my work when Opus 4.8 will just automate it and even faster. If Opus 4.8 does automates some component of research, all the better. I really like this quote from Peter Medawar that as scientists, the business we're in is not about struggling on problems, it's solving problems. So if there's a new technology that makes us solve if I have a theory of intelligence and an AI can help me create it, if we can solve the Riemann conjecture with AI, like, wow, that's our goal. We have to use it. Like, it's all the better. It's just, we can do even more. So just set your ambition for understanding even higher as things become more powerful and automated. And that's my response to not wanting to compete with like soda performance.
I think it's a great statement to finish. So Philip, do you have anything else that you want to add?
No, yeah, I think that was some optimism toward like what fun we can have in just like the pursuit of knowledge. I think that's maybe what I'd like to end on.
I'm very similarly optimistic about AI's potential.
Yeah.
Me too. So Philip, thank you so much for coming. It was a real pleasure to have you.
Thanks so much for having me. Yeah, it was really fun.
Thank you, everyone.